Thank you very much. Hiya. I should also mention that because Steve Faulkner, my friend, couldn't make it, I stole his identity at the start of the conference. So I'm also Steve Faulkner. So I work for the W3C and I edit HTML and ensure that HTML is more accessible. So if we can get a big hand for me, Steve Faulkner, as well. I was just going to say, I'm Steve Faulkner, I'm a poo head or something like that, which would be a bit unfair. I just need to do a little sound test here. This is just a little something I've been working on for the Kellogg's company. Just trying to get the levels right. Can you hear me over the sound?
Hello and welcome to today's programme. Cornflakes, Rice Krispies. Only joking.
Right, okay, that seems to be normal. Well, for certain versions of the word normal. My name is Heydon. I'm not Steve Faulkner, I am called Heydon. It's quite a good name, actually, because it means that I can sometimes have a username which is just my name, Heydon, because that's a slightly weird spelling. So I'm at Heydon on CodePen. Don't follow me on CodePen. It's just a load of crap on there. There is some disambiguation to take care of, though. Naming things is hard. They do say that in programming, the two hardest things are naming things and cache invalidation. I don't even know what cache invalidation is, so that's going to be even harder for me. But I'm not Heydon Pickering, who's pictured on the left there, who, if you don't already know, is a famous node hacker from Cornwall. And I'm also not Hayden Christensen, who is he started out as a UX designer, and then he turned to the dark side and became a social media marketing strategist. So I know that there's only three Heydons. I'm not those two, so that's just sort of process of elimination. But I do have one thing in common with those other Heydons, and that is that none of us are really known for our mathematics. None of us are really known for either talking about mathematics theoretically or applying mathematics to anything. And so it would be easy for me to feel really nervous today, standing in front of you for about 40 minutes talking about mathematics, which is mostly what this talk is about. But then I think of one man who's a great inspiration. I say a man, he's more of a sort of a being. And I channel him, and he comes down into me and into my heart and makes me feel peaceful and confident, because this man has really made it his own. He's really set the standard for talking about things he knows fuck all about in public places. And this man is Michael Gove, our former education secretary, who famously was asked during a public consultation to justify a remark in which he said that all schools in the country should be able to perform better than average. Better than average, just to be specific, in case no one's got that yet, better than average for all schools in the country. So, and of course he tries to solve that by introducing another variable, time, so he's sort of clutching at straws there. But if he's able to get up and talk about that in television interviews and all sorts, then I feel quite comfortable talking about it today in front of you. And, I don't set policy for millions of children, so that's good. So it's going to be pretty basic mathematics. It's enumeration, which is simply getting more than one thing, which is like other things, and putting them in the same place and going, there is some. Divisibility, which is small sets of things, and putting them in larger sets and seeing how many small sets fit in the larger sets, which is also pretty simple. And prime numbers, which is any numbers divisible by only one and themselves. And they have some odd properties. I'm going to apply that to sound design, because I do a bit of sound design, some animation, so I'm going to be covering that as well, and CSS layout too. But first, I'm going to talk to you about Swedish Death Metal, which is a bit tenuous, it seems, I think. I just did a talk in Sweden. I didn't do this slide, and I didn't talk about Swedish Death Metal there, which is where it obviously comes from. It's a much maligned musical genre, death metal. I think a lot of people who aren't familiar with it, with the ins and outs of it, see it as just sort of bluster. It's just sort of, Satan, and that's it. And it doesn't take a hell of a lot of talent or poise. But that couldn't be further from the truth. Whether or not you like the brutal aesthetic of death metal music, it's actually very precise and complex in its construction, and it takes a lot of dexterity to play as well. And Meshuggah took this one step further, or did something more interesting with developing the complexity in their sound, in that they employed some mathematics. And the reason they're called Meshuggah is it's from the Yiddish for crazy. And when you listen to them, it's a bit like listening to a sort of a fractal. It's like being sucked into a vortex, because the things sort of overlap in unexpected ways. There's a sort of a sense to it, but there isn't a sense to it. It's sort of mind-bending. But you don't have to understand mathematics or even kind of get it cognitively that you're being sort of fucked with by this band, because it affects you physically. It's sort of somatic. Basically, if you try and dance to it, you look like a drunk dad at a wedding. And I'm going to demonstrate that for you now. I'm going to really, really regret this, I think. And my microphone will probably come off, and then the whole thing will be. So if you just imagine I'm at a wedding, I've been having a sort of chat with some people, I've had a few gin and tonics or whatever, my daughter's just got married, and then someone, the DJ, naturally, after they've put on, I don't know, Ride Sally Ride or something, they put on a bit of Meshuggah, so you come onto the dance floor like this. And if you just listen to how everything's sort of flowing over itself in a very strange, I don't know what I can't dance anyway, so this is nonsense. Anyway, so yeah, I did regret that. So what was going on there, which should be the next question. What they've employed is some polymetric syncopation. Polymetric literally means of multiple lengths. So what they're doing is the different instruments are playing parts which are of different lengths, but they're playing them at the same tempo. So they're sort of syncing up in terms of time, but then they're sort of overlapping and ending and finishing at different times. So I've just made a kind of a simple version of this. So this is just using a 4-beat pattern and a 3-beat pattern to make a composite polymetric pattern. And that works a little bit like this. So this is the 4-beat pattern just played on its own. So I just made this in a sequencer on my computer. So it's 1, 2, 3, 4, 1, 2, 3, 4, etc. So like most pop music, blues or whatever is sort of made around that. And this is a 3-beat pattern, but it's the same tempo. It's 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. And now I'm going to bring in the 4-beat pattern behind it. Now, I'll probably screw this up the first 2 or 3 times because of the lag. There's a bit of latency in sort of sound engineer terms, because I'm doing this with JavaScript. Not quite there. So you can hear the composite pattern that's made. Now, I'm not changing either the 3-beat pattern or the 4-beat pattern, but together they create something more complex. So from something simple, we have something more complex. And there's an axiom that governs this. And in mathematics, we have axioms, and they're sort of true statements based on certain conditions. In this case, the length of a polymetric pattern is the lowest number, the lowest integer, divisible by the length of each of its parts. And so when it's 4 repeated patterns of 4 over repeated patterns of 3, then the length of the combined pattern will be 12, because 12 is the first number divisible by both 4 and 3. So from that point onwards, it will repeat itself in 12-beat intervals. And that's pretty easy to sort of cover if you've only got 2 parts and 2 numbers. If it's more complex, you might want to use some programming to sort of extrapolate it. So I wrote a bit of JavaScript here, and it's quite simple JavaScript. The lengths, the constituent lengths, I've put into an array. So in this case, in the example 4, 6, and 9. Then there's a denominator, like an incrementer, you know, like when you do a plus plus. And then I increment that number, and each time I run a function which tests to see if it's divisible by all 3 of those numbers. And if it is, it then stops, and then the output would be the length of my polymetric pattern. And so then I created something graphical to express this. So I believe I did 4, 6, and 9, so I just entered them here. And it sort of looks like a sequencer, like in Cubase or something like that. And there's 2 things I noticed about this, one of which was unexpected to me, and that was that it's symmetrical. So if I put in any numbers, it doesn't matter what the parts are, or how long they are, or how many there are, this pattern, the visual pattern that I've created, which represents how the music interacts, the relationships in the music, will always sort of fold back on itself. And that's just one of those innate, weird, beautiful things about mathematics, I think. The other thing I noticed is that if I use prime numbers, then the overall length is much, much greater, even though I can just use numbers of a similar magnitude. So if I use 3, 5, and 7 and do the same thing, I've actually got to scroll here and show you the whole pattern. So at 120 BPM, this piece of music is unrepetitive for its entire duration because the relationships between the different parts are constantly changing until the very end where they finally sync up. And that's nearly a minute long. If I add another prime number in there, I've now created a piece of music which is essentially prog rock. It's 9 minutes long, and it doesn't actually at any point repeat itself because it's constantly shifting until it finally reaches that 9.625 minute mark. Prime numbers are used in other areas of web development and security. I don't really understand RSA encryption very well, so anyone can correct me at the end, but I gather that the idea is basically about the fact that encrypting is easy and decrypting is hard, because when you encrypt something, you're just taking 2 prime numbers and multiplying them together. And that's no harder than taking any other number and multiplying it together. But when you're factoring the result, that's finding the 2 numbers which were used to encrypt. It's much harder, it's much more computationally heavy, which means it's more of an arse ache for the people who are trying to hack. Yeah, that's RSA encryption in a nutshell, I guess. Even cicadas know more maths than Michael Gove, for instance, and myself. And they appear to actually do their gestation periods, their life cycles, around prime numbers. So biologists observe that in different parts of the world, you'd have one brood of cicadas, or cicadas, depending on how you pronounce it, which did their life cycle in 11-year periods, one in 7, one in 13, I think. And it makes perfect sense. And just with the music, it's all about the fact that they don't sync up with the rest of their environment so much. So with other animals having their cycles around normal numbers, even numbers, or normal odd numbers, not prime numbers, there's less convergence. So it's less likely that they'll emerge, which they do en masse, which is a very noisy and spectacular thing, when predators are at large, which are more likely to eat them in large numbers. So, a bit more music now. I've done a sort of death metal bit of divisibility in prime numbers through Meshuggah. And what I wanted to demonstrate now is how you could actually create an entire piece of music just through simple sounds being triggered at certain beats. So I created 3 chords. They're simple chords just of 2 notes. And when they're played together, they do harmonize. So the 6 notes together makes a chord which works. And either of the 2, so it would be a set of 4 in each case, that would also work. So the first one sounds like this. And that's played every 3 beats. The second, like that, and that's played every 5. And the third, which is played every 7 beats, sounds like this. And when you play them all together, and just set them off like that, and I did this just in Cubase to start with, but I'll show you how to do it later with HTML and JavaScript, it creates something like this. So not only is this a piece of music which at no point repeats itself, it doesn't become repetitive like a piece of pop music. I say a piece of music, it's more like a soundscape or something like that. But there are also peaks and troughs in terms of amplitude, because sometimes 2 of the chords will play simultaneously, and because they're playing simultaneously, that's more sound. Now, you could think that perhaps playing 2 sounds of the same amplitude together would double the volume, but that's not true. It has to be orders of magnitude. So you'd have to play the same sound, you'd have to play 10 of the same sound simultaneously for it to be double the volume. Now, this is awkward because this is generative, and I don't know how long this is going to last. I think I'm just going to quickly go and get a coffee, I think, and then I'll come back. Is he still on? Oh, fucking hell. This is awkward now, isn't it? I'm sorry to have left you in a room alone with Michael Gove. I think it's about 2 minutes altogether. But it's 2 minutes of music which is very, very easy to generate because I've just set things off. That's what people mean by generative music. So you get a computer to do it for you or a mathematical algorithm to do it for you instead of you actually sitting there with a guitar and going, that's how I'd like to play it. Okay, so bye-bye, Gove. Right, so there's a sort of inherent performance thing here. And as I was experimenting with this for the talk, I thought, well, hey, what I've got there is, because I'm repeating individual sounds rather than it being a whole sound, like the duration of that song isn't a 2-minute file, there's an inherent performance thing there which I could try and exploit. So for the 15 seconds of actual sound that I might download, or a client might download in their browser, I can actually create 10 times almost that amount of music. So it's a sort of a form of making music or making sounds that's its own compression algorithm. So how would I go about doing that? With a little bit of HTML5 and JavaScript, basically. So I'd have audio elements, give them IDs so that I can reference them in the JavaScript, and obviously a path to the actual sound file, in this case OGG, but you'd probably want to support other formats because browsers are a bit inconsistent. Name that, and then just use a set interval function. So you can see the window.setInterval there, and then every 3 seconds or every 3,000 milliseconds it would play that one sound. But of course, once it's downloaded the sound, it's then repeating it. So you're not actually front-loading it with lots of information that the client has to download. I've commented out the sound name.play just above there. You could get all the sounds in your Polymetric music to play simultaneously first and then get them to repeat at their different intervals. But then you get a sort of a loud sound at the beginning, which isn't so hot. Stopping further repetition of the sounds, you just call the clear interval function in JavaScript and just supply the name of the repeater that you'd set off in motion before, in that case the one which is every 3 seconds. And the cool thing about that is you get these sort of clean diminishes as well. You're not just stopping the sound dead, you're letting each individual sound play out in its own time, and then they will end at different times, and then it just doesn't start again. So all of this simplicity gives you something which is quite, sounds quite rich, I'd like to think anyway. So how would I apply this visually? So the same sort of underlying mathematics now, but I'm going to apply it into a sort of a visual context. And of course, you could do some CSS animation, and there's the animation duration property, which allows you to set how long each animation lasts. So I've just used nth of type there. I'm going to talk a bit more about nth of type and things like that in the CSS layout section of the talk. And what I've done is I've said, take these objects which are alike and make each one their animation last a different length. And it took me a long time to think of something compelling to show you how you could apply that, so what to animate, and I thought of clouds and things like that. And eventually, and inevitably, I landed upon whack-a-mole, which, so I drew a little mole here, and if you've ever played whack-a-mole, you have moles which come in and out of holes like that, and you have to hit them with a hammer. And then you win the game, I guess. I guess you've got to hit as many as you can. So, exactly the same JavaScript behind what I did for the sequencer, but in this case, I'm going to put a few moles in there. I'm going to just start with one which goes every 2 seconds and one every 8. So this would be really easy for someone who's playing whack-a-mole to work out. So that one always goes that amount of time, and that one. The relationship is repetitive much quicker. Whereas if I was to use prime numbers again, the overall, okay, I have to zoom out, I think. 3, 5, and 7. Why is that not working? Oh, he's underneath. Okay, this because the screen's a bit different. I didn't anticipate that. So basically, if you're using 3, 5, and 7 intervals, then the overall game, like the piece of music that I played, will be much longer before it starts to repeat. So for that whole duration of that time, it takes ages to really kind of work out what the pattern is. It's constantly, you have to second guess it, I suppose. And then I just added one more variable. I'm just going to show you that here, actually, which is a difficulty variable. So when I start the game again, now you can see that it's much more difficult to catch the moles. Oh, that helps if I do that. But now I can't click on them. I've got a dilemma now. I think I'll move it on. But anyway, you can see they're moving faster. And what I've done is I've applied the same, changed the same variable across all the moles, and it's a really simple thing to do. All I've done is change the distance that they have to cover. So the first example, the easy mode is on your left there, and on the right is the difficult mode. And this is really simple sort of primary school, possibly middle school mathematics. They're traveling the same distance in the same time, but because they have to travel a further distance, they have to go faster to cover it, which means that the moles spend less time above ground proportionately. So it's just speed equals distance over time. And in this case, if you're interested in the code, I just changed the translate Y property for all the moles. So design versus aesthetic. Now, when I built the whack-a-mole game, I was thinking to myself, well, this is really fun, but the design of it is really the mathematics underneath. That's the sort of the algorithm which governs it. And that, to me, is what design's about, and that's the important part. But there's a lot to be said for aesthetic as well. There was a guy called Tim Hunkin, who's an engineer. He actually took an old whack-a-mole game, and he gutted it, and he took the mechanism out. And the mechanism works exactly the way that it would have done originally, but he just changed the theme. He made it political. He turned it into Whack-a-Banker. And the thing that I really like about this game is that instead of it now saying insert 40p, it says minimum investment 40p on the game. So I thought that was quite a cool joke. I've done a similar thing here in that I have made a predictably whack-a-gove game here. So you can see me whacking Gove on the head. And I think that says something about aesthetic, because I'm not really that inclined to hit a small, innocent, wouldn't hurt anyone rodent over the head. But I really fucking like hitting Gove over the head. So I'm better at this game, despite the fact that it works in exactly the same way and everything happens in exactly the same sequence as you've decided it. I'm actually better at this game because I'm more inclined to use it. So I'm going to put together some of the ideas I've talked about so far with the animation and the sound. I'm going to do a demo now on my laptop, which hopefully won't burn out, which combines those ideas. And when I was making this, I was thinking about a game called Monkey Island, which, if you're as old as me, you may remember playing. It's a sort of problem-solving game where you go from scene to scene, and you sort of try and solve puzzles as you go along. And I spent a lot of it, because I'm quite slow, I spent a lot of this game standing around trying to work out what the puzzles were and just looking at the screen. And what was nice is there was always little animations going on to keep it looking alive. So you'd have someone blinking, or a fire flickering, or blades of grass waving, or whatever. And it occurred to me that the clever thing that was going on here, although I'm not entirely sure they actually did this, but they could have done, is that if it was one set animation where the grass and the blinking and the people twitching their leg or whatever was all happening as part of one animation which then repeated, you'd start to see that it was repetitive. Whereas if you governed all of these animations independently, it would work a bit like a combination lock. So in a combination lock, if you just had one wheel, then it would just take 10 attempts to work it out. Or you wouldn't even have to work it out. You just go through the motions until you opened it, right? Then if you had another one, it doesn't make it twice as complex. It makes it 10 times as complex. And with 4, it would take potentially 10,000 attempts to work out how to open that lock. And it's the same thing with using concurrent animations, which aren't actually connected to each other, because they're moving independently. You're multiplying rather than just adding complexity. And to demonstrate this, I have created a sort of a scene where the music now in my browser is going to be playing and repeating in the way that I described using a set interval. And there's going to be a number of CSS animations which all happen in the same space but independent of each other as well. It's just going to take a couple of minutes to come in. This is a different sort of theme to the whack-a-mole thing. It's a little bit more dark and disturbing, I suppose. So you can see flickers happening on the screen, but those flickers are happening independent of each other. It's not a flickery animation. This is not a video of an underground car park camera. It's a living thing with lots of different things happening independently. Because there's so many, like the record button, the shutter, the different flickers, the lights flashing and everything, the overall length of this animation, despite the fact that there's only a few parts, could be days or weeks or even years before it actually repeats itself. This was inspired, by the way, by the film The Grudge. And there's a bit in, I don't know, hands up anyone who's seen the film The Grudge, the Japanese horror film? Yeah, and there's a bit where there's the ghost character sort of approaches the camera, you know, with a thing like that, comes up to the camera, and it's really, really frightening. And so I've tried to incorporate something similar, and that only happens every so often. So I'm going to do another poll here. Who here has a heart condition? Okay. Could you, if you put your fingers in your ears or close your eyes? Actually, to be honest with you, that happens so infrequently, the chances are that I would run out of time talking before it even appeared, so there's no... Of course, Gove sticks his fucking face in where it's not wanted, as usual, so that's that. So there's another great takeaway. So maths and CSS layout. I've been writing lots of articles for Elista Part recently about some weird CSS techniques, and the last one was called quantity queries. And it's all about combining different selectors in ways that you can achieve strange effects. So I'm going to talk a little bit about that now, and particularly employing the divisibility idea that I've used in the animation and also previously in the all of the Gove stuff, basically. The nth child selector family, or nth of type as well, and the nth last child, etc., they're sort of inherently mathematical because they take an argument which is arithmetical or sort of algebraic. So the very simple example, which I'm sure a lot of you may have used to do CSS, is just putting a number in there. So if a set of elements, of sibling elements, nth child 3 would mean just select the third of that set, the third from the beginning. Nth child n plus 3 is sort of an offset. So it's saying all of the elements, but starting from the third. So it's all n, but we're going to start at this point, the third one. So it would select the third one, then the fourth, and ad infinitum. Then you can do sort of multiples. So 3n would be like the 3 times table. So 0, 3, 6, 9, 12, etc. And then you can combine some of these ideas. So you can do 3n plus 1, which would mean the 3 times table, but starting at 1 rather than 0. So you'd actually have 1, 4, 7, 10, etc. And you can combine these together. You can concatenate them. So by doing that, you can actually achieve some really strange things, like styling by quantity. So I'm going to just use 2 conditions in this first example, and I'm going to add elements and remove elements, but I'm not adding any JavaScript or anything, or adding any classes in there which determine how the elements look. It's just the CSS logic. So if it's the third last item and it's the first item, what would we expect? If I add that element, there's no match there. It doesn't meet any of those conditions. Or it does actually meet the first item condition, but it doesn't meet the third last item condition. So that's not selected. Then I add one, and there you have the third last item, which is also the first item. Then if I add another element, of course, the third last item is no longer also the first item, and so you've run out of things. So what's interesting there is that you've styled based on quantity, really, because only when there's 3 can the third last item also be the first item. And the code looks a little bit like this. So we use nth last child, 3, and we concatenate it, so there's no space between those two, with first child. And then we're just making it background green, which in practical terms isn't, very useful, but it's just to demonstrate here. And concatenation is indeed the name of a Meshuggah track, so just showing their mathematical credentials once again. So how would I style all the items? So what if I wanted to style all the items in the set based on the quantity of that set? So doing that, it would look like this. There's 3 items there, and all of the items are now green because there's 3 of them. That's the condition. And then when there's 4, it's no longer the case. So that looks a little bit uglier, and I've had people complaining to me that my CSS was ugly. I don't think you can do it in any prettier way, except that there have been some folks doing some post-processor stuff to just make it look a bit better and using Sass. But the logic that actually is behind it is here, and that's nth last child, 3 first child. So it styles that first one already. And then it says, also, take this one and style, if that one exists, style all of the ones which appear after it, which is using the general sibling combinator there. I don't know if you've used that before, but it just says, we've got our element here, just all the rest, and do that. So you can also style by divisibility, similar principle, but instead of it being enumerating, it's more to do with what the set is divided by. So I think of it a bit like this. I think of it in terms of frogs either landing on their lily pads or landing on the rocks and dying. Maybe that's just the way my brain works. But if you imagine using nth last child and you're stepping backwards using multiples, if there's 6 items or there's 9 items or the number of items is divisible by 3, then as the frog jumps back, it will land on the first of those lily pads. If there's 5 or there's 7 or it's not divisible by 3, it won't ever land on the first one. So you can sort of use this to try and govern grids, I suppose, CSS grids, so that when the content changes, it actually reconfigures itself intelligently so that it won't be uneven at the bottom. There won't be any gaps. So the first block at the top there, nth last child 2n, first child, blah, blah, blah. So you can see I'm using the multiples there in the argument for the nth last child. We'll make the cells in the grid 50% width, so they're 2 by 2. If the whole set is divisible by 3, then we should divide it into 3. So we'll do them 33% width and 25% for if the set is divisible by 4. So you start to get effects like this. So there's 1. So that defaults to 100% width because block level elements will always just fill the space. There's 2. There's 3. There's 4. No problem so far. 5 is a prime number. So talking about primes again, but primes are gonna fuck us over a bit this time. They're going to be a problem to solve rather than something which is a handy tool. There's 6, so 6 is divisible by 3, so it goes, hey, it's divisible by 3. It meets the second block in our CSS and divides it by 3, and it looks nice and neat. 7 is another prime number, bugger, and then 8, so 8's divisible by 4, so 2 sets of 4 there. 9 divisible by 3, 10 divisible by 2, 11 is a prime number, and I've screwed my slides up because of that. Right, so how do we handle the primes? We have to do something a little bit more intelligent, and what we really have to do is we have to take what we have and divide them into further subsets. So the way I would go about doing that is like this. So if it's divisible by 5, we start out by saying, well, hey, let's make them 3 by 3, but then we're going to have to handle the last 2 differently. So the last 2, we say, we use the offset. So we have the 5n plus 4 means the 4th of every 5. So for every 5 in the set, the 4th will be styled 50% width. And then we just use the adjacent sibling combinator there with the li and say, well, the 5th one also should look like this, and the 5th one is the one next to the 4th one. We've done a similar thing with 7 items, so the next prime number, and we've started off doing it 3 by 3, and then we just do 100% width for like the spare one. So 1, 2, 3, 1, 2, 3, 1. So now my grid system handles a few primes, so it takes longer to break, I suppose. So 1, 2, 3, 4. 5 is divided into 3 and 2, so that's still neat there. 6 is divisible by 3, like in the old version. 7, you've got the spare one sorted out. 8 divisible by 4. 9 divisible by 3. 10 is now 2 sets of the already subsetted 5, so 3, 2, 3, 2. And 11, we still haven't handled. So the question is, how many prime numbers would I have to take care of in order for my grid system to be infallible, for it to work in every case? And a mathematician called Euclid, in 300 BC, when he was working on the first ever CSS grid system, looked into this and did some conjectural mathematics and proved that the number of primes that exist as you count up is in fact infinite. You wouldn't think that it would be infinite because you'd think that the larger the number, the more chance there would be that that number would be divisible by something, right? But that's not the case. You still get huge prime numbers, hence the RSA encryption thing working. So I would have to write an infinite amount of CSS in order to make an infallible grid system, which would have some implications on performance. So as you can see, Euclid is, he's done basically, and I'm kind of done as well actually. I've covered all the maths I know, so I'm just going to sort of finish up just with one last thought, which is that maths doesn't govern the universe. I hear people, sometimes even mathematicians, say maths governs the universe, and they say, without maths, it doesn't work. But the thing is, maths is a human construct. Dinosaurs didn't have maths, and yet they were still subject to the mathematics which expresses the natural physical laws. The truth is that the universe isn't governed by maths or anything else. It's just inherently boring and easy to predict and sort of ordered and symmetrical. But what maths is a language which helps us to exploit that commonality and predictability. And even possibly, we might be able to make an infallible self-correcting grid system one day. Thank you very much for listening.